Hi, welcome back to educator.com, and today's lesson in general chemistry is going to be our second lecture on stoichiometry. Okay, let's go ahead and look at the lesson overview. So last time we laid out a pretty good foundation for how to tackle stoichiometry problems. And so we're just going to now build upon that foundation and apply stoichiometry to more specific cases. These cases include the following. We're going to first talk about solutions and their concentrations. Okay, and we're going to work with a lot of terminology today, such as molarity and dilutions. After discussing molarity and dilutions, the next specific application of stoichiometry is going to be to double replacement precipitation reactions, acid-base neutralization, and finally something we have not talked about yet, which is called acid-base standardization via a titration. After that, we'll go ahead and do our summary followed by our sample problems. Okay. Moving on now, molarity. We tend to think of a solution in chemistry as composed of two items, typically a solute and a solvent. The solute is going to be present in the smaller quantity, and the solvent is going to be present in the major amount. And of course, for general chemistry lecture and for laboratory, the typical solvent, of course, is going to be water. Okay. And we always like to express a solution's concentration. Basically, how much solute we have relative to solvent. And so there's a lot of different units we can use, but the most common one we're going to use is called molarity. And the equation for molarity is defined as the following. Molarity is equal to moles of solute for every liter of solution. So from this equation, of course, we should always be very comfortable with solving for a single variable. And so we can solve for liter of solution, and that's going to be basically moles of solute over the molarity. And of course, we can also solve for moles of solute. So moles of solute is just going to be equal to molarity times liters of solution. Okay, so once again, you want to definitely have these equations committed to memory, especially for general chemistry. Let's go ahead and jump right into a calculation. Okay, so how many grams of potassium bromide are needed to make 350 milliliters of a 0.67 molar KBr solution? So when we verbalize capital M, which stands for molarity, this is verbalized as molar. Okay, so this is the language, this is the terminology that we use. So 0.67 molar potassium bromide solution. All right, so this is a first example, and we're just going to plug everything we know into the equation for molarity and solve for the unknown. Okay, so the molarity is given to us. That's 0.67 molarity, and that's equal to moles of solute divided by liters of solution. Okay, we don't know what the moles of the solute is, the moles of KBr, so that's going to be what we're trying to find. And the liters of solution, you're actually told that in the problem. It's here. It's 350 milliliters, which is 0.350 liters. All right, so when we go ahead and solve for moles of potassium bromide, we get 0.2345 moles of KBr. And of course, you see that the question is not asking for moles, but the question is asking for grams. And do you recall how to go from moles to grams? What's the conversion factor called? It's molar mass, right? Okay, so 0.2345 moles of KBr times something over something, and that's going to give us the grams of KBr. All right, so the molar mass is approximately 119 grams over 1 mole, and we're going to get an answer of approximately 28 grams of KBr. All right, so we are really playing on the concept of the mole very heavily. So once again, what we learned last time in stoichiometry is going to serve as our foundation for the rest of this lecture. So it's very important that we have those fundamentals down. All right, now, let's go ahead. Now, what we just did was we used the molarity equation directly, moles over liters, and we just solved for the unknown. But there's another way of using the molarity equation. And you see that the equation for molarity is basically a ratio of 2 units. And if you recall, I've said this many times before, that when you have a ratio of 2 units, you can get a conversion factor that can be used in dimensional analysis. All right, let's go ahead and use this approach now. So you see this is the exact same problem as before. How many moles of KBr are in 350 milliliters of a 0.67 molar potassium bromide solution? And how many grams is this? All right, so remember how we tackled dimensional analysis? Okay, you always start with the unknown. So what's unknown? What's the only thing that's given to us that's not part of a ratio yet? Well, 350 milliliters is by itself. That looks pretty good. And 0.67 molar. Remember, this is a ratio of 2 units. This is really 0.67 moles for every 1 liter, right? Or this is going to be 1 liter over 0.67 moles. So remember, this is how we use molarity as a conversion factor. So it's going to be moles over liters or liter over mole. All right, so let's start with what's given to us that's not part of a ratio, and that's going to be 350 milliliters. And you see that in the equation for molarity, the volume is actually liters. And so what do you think we have to do to 350 milliliters? Right, we got to get it to liters. So that's going to be 0.350 liters times something over something. Okay, so let's go ahead and use our conversion factor. So we want liters downstairs and we want moles upstairs. Okay, so that's going to be 0.67 moles for every 1 liter. And that's going to give us our answer of 0.2345 moles of KBr. And from there, you can go ahead and get the 28 grams of KBr on your own. Again, all this is the exact same problem we just did about a minute ago, but all we're doing is now we're using molarity as a conversion factor instead of just using the equation itself. Either way, whatever is more comfortable for you, please use that way. Now, let's go ahead and move on. What volume in milliliters of a 0.67 molar KBr solution contains 250 milligrams of KBr? All right, so we see molarity here, and we know that molarity is 0.67 moles over 1 liter. So we're not going to start with that because that's a ratio already. So the only other value is right here, 250 milligrams, okay? Remember what we have always done in stoichiometry. We always wanted to get to moles, right? Everybody remember grams to moles. Okay, that was so typical of being the first step in all of our problems, this lecture and last lecture. So anytime you see mass in a stoichiometry problem, we're always going to get it to grams and then to moles. So 0.250 grams of KBr, okay? And we're going to go ahead and get this to moles of KBr, so that's going to be times 1 mole divided by roughly 119 grams of KBr. All right, so that gets us moles of KBr. And now that we're in moles, we can use molarity as the conversion factor once again, the 0.67 moles over liters. Okay, this time to get canceled goes moles, liters goes upstairs, and so it's 0.67 and 1 liter. So that gives us our answer in liters after all is done and canceled. And now I want to get to milliliters, of course. So times 1 milliliter over 10 to the negative 3 liters. And so this is going to be an answer of 3.1 milliliters, everybody. All right, so once again, any stoichiometry problem, everyone, always get the moles. That's always should be your first step. So you're going to hear me say that quite often. Once again, for stoichiometry, the first step is to get anything you can into moles. All right then. The next application of stoichiometry, and this comes directly from molarity, is the practice of what we call the dilution. So when you order a chemical from a company, the chemical typically comes in a bulk form, and it's typically very concentrated. This is what we know as the stock solution. And so when you receive the stock solution, you typically dilute it down to a desired concentration. So being able to do a accurate and precise dilution is quite important in a laboratory setting. To perform a dilution, the equation here is going to be used. It's basically M1 V1 equals to M2 V2. Okay, where M1 is the initial molarity and V1 is the initial volume. M2 is final volume molarity, and V2 is the final volume. Now, when you do a dilution, you typically just add water, right? So for example, sometimes parents, when they give apple juice to their children, they typically add water to dilute it down. So notice though that the only thing they change is the amount of solvent. They do not change the amount of juice or sugar. So the amount of solute remains the same. Okay, so amount of solute does not change in a dilution. And we can prove this mathematically. Because when I take molarity, which is moles over liters, and I multiply by V1, which is liters, look what I get at M2V2. M2 is moles over liters, and times liters. And so moles is equal to moles. And so once again, everybody, in a dilution, the moles of solute before equals the moles of solute after. All right. So we're now going to get into a typical dilution problem. Okay, explain how to make 250 milliliters of a 0.67 molar potassium bromide solution, starting from a 1.2 molar stock solution. All right, so let's go ahead and write out the equation again. So M1V1 equals to M2V2. All right, so let's see what we can plug in now. M2V2 is already given to us. M2 is going to be the desired concentration of 0.67 molar. V2 is the desired volume, and that's going to be 250 milliliters, or 0.250 liters. All right, the M1 is given to us also. It's the 1.2 molar stock solution. So this V1, therefore, is the unknown, everybody. Now, it's pretty simple to solve for this algebraically. And so after we're going to do this, we're going to then discuss the physical significance of this, because that's another issue. So V1 is going to be 139.6 milliliters. All right. Now, what is the physical significance of this volume? Okay, so this is the amount of the stock solution you're actually going to take. So amount of stock solution to dilute. But how much water do you add then to dilute it? Well, if we want 250 milliliters as the final volume, and we're going to use 139.6 milliliters of the stock, all I got to do is subtract. And so V final minus V initial is going to give me the volume of water to add to perform the dilution. And so that's going to be equal to 110.4 ml of water. So if you were to do this physically in a laboratory, you will literally take 139.6 milliliters of stock solution, and to it you would add 110.4 milliliters of water, and that's going to give you 250 milliliters of the 0.67 molar potassium bromide solution. Okay? So once again, this is how you do a standard, typical dilution problem. All right then, let's move on to the next application of what we learned last time in stoichiometry. And the good news about this is going to be all familiar. So this is stoichiometry and double displacement precipitation reactions. All right. So, before, we tackled the following questions. How many grams of lead chloride can form from 50 grams of NaCl? We know how to do this. We went from grams of A to moles of A, and then to moles of B, and then on to grams of B. Everybody remember this is what we called a mass-to-mass conversion. Okay, so mass-to-mass conversion. Okay, now we're going to change it up a little. And all we're doing is we're asking the same problem, but now we're going to incorporate molarity. So now, how many grams of lead 2 chloride can form from 250 milliliters of 0.32 molar NaCl? All right. Remember, what's always the first step in the stoichiometry problem is to get to moles. All right, so get to moles. All right, so we have 250 milliliters and we have 0.32 molar. We have a volume and a molarity. So we're going to take 0.250 liters. We're going to multiply that by something over something, and that's going to give us moles of sodium chloride. So liters goes downstairs and moles goes upstairs. And that's going to be 0.32 over 1. All right, so that's going to give us moles of sodium chloride. Now, what we want to do again is grams of A to moles of A to moles of B to grams of B. Okay, we're still going to follow that flow chart. So now that this is really our moles of A. Okay, so now we're going to get to moles of B. So we're going to take X moles of NaCl. And everybody remember how we get the mole-to-mole ratio? It comes from the balanced chemical equation. So 2 sodium chlorides to 1 lead 2 chloride. So that's going to be times 1 mole of lead 2 chloride for every 2 moles of sodium chloride. All right. That's moles of B, and now for moles of B, we go on to grams of B. So now multiply by the molar mass of lead 2 chloride, which is 278.1 grams of PbCl2 for every 1 mole of PbCl2. And when all is said and done, we get 11.1 grams of PbCl2, everybody. Okay, so this is a very typical problem, everybody. And don't forget, what we did here was the following. Basically, volume times molarity gets you the moles. I cannot underscore this enough of how often you're going to use this when you do stoichiometry problems. Remember, volume times molarity is equal to moles, and it's going to be typically your first step. All right then. Now, let's do another problem. Okay, so how many grams of lead 2 chloride can form when 250 milliliters of 0.32 molar sodium chloride and 150 milliliters of 0.45 molar lead 2 nitrate mix? Okay, so you notice that you are given amounts of both reactants instead of just one. Remember what type of problem this is? Anytime you're given amounts of both reactants? That's right, it's a limiting reactant problem. So the limiting reactant problem that we learned in the previous lecture can easily still apply to what we learned today. Let's go ahead and do it. So everybody remember we're going to use what was called the smaller quantity method to solve limiting reactant problems. So let's go ahead and do this. So remember, we're going to determine the amount of product that can from each of the reactant amounts. All right, so 0.250 liters, and this is going to be times 0.32 moles over liter of sodium chloride. Okay, we want to get to lead chloride. Remember, it's a 1:2 ratio. We just did this. All right, and so that's going to give us 0.040 moles of lead 2 chloride. I'm going to repeat the process now for the other reactant amount. So 0.150 liters times 0.45 moles of lead 2 nitrate over 1 liter of the lead 2 nitrate. And when you look back at the balanced chemical equation, the mole-to-mole ratio between lead-2 chloride and lead-2 nitrate is 1 to 1. So times 1 mole of lead-2 chloride divided by 1 mole of the lead-2 nitrate. All right, and when that is all calculated, you get 0.068 moles of lead-2 chloride. So in this specific example, the theoretical yield should be 0.040 moles of lead-2 chloride, and that translates to 11.1 grams of lead-2 chloride, everybody. Therefore, the limiting reactant in this specific example is sodium chloride. All right, so again, everybody, we're using previous learned material in today's lecture, and that's all. It's just a slight twist on things, but you're totally capable of doing this. Again, it's just using old material. That's kind of the nice thing about this chapter, about this lecture. We're really building upon what we've learned just recently. All right, then. The next specific application of stoichiometry is going to be to, again, another aqueous reaction that we've already talked about, and that was the acid-base neutralization reaction. If everybody recalls, in a neutralization reaction, it is always between an acid and a base, and the two products are always going to be water and a salt. And again, a neutralization reaction between a Bronsted-Lowry acid and a base is just another double replacement reaction. And this equation is balanced, so we're good to go and ready to use it. So how many grams of sodium hydroxide are required to neutralize 4.5 grams of hydrochloric acid? Once again, grams of A to moles of A goes on to moles of B, goes on to grams of B. All right, so this is a typical mass-to-mass conversion again, everybody. Don't get thrown off by the word neutralize. Okay, it's just another term there that means it's going to react with each other. All again, this is just a mass-to-mass conversion. So 4.5 grams of hydrochloric acid times 1 mole divided by 36.458 grams of hydrochloric acid. Okay, that's its molar mass roughly. So that gives us the moles of A. Okay, moles of A to moles of B, so that's going to be a 1-to-1 ratio. So that's 1 mole of sodium hydroxide over 1 mole of the HCl. And finally, now we're in moles of B, so let's go ahead and move on to grams of B. So that's going to be times 39.998 grams of sodium hydroxide over 1 mole. And so 4.9 grams of sodium hydroxide are required for this reaction to proceed, are required to neutralize the indicated amount of hydrochloric acid. Now, we're going to tackle the same problem, but now we're going to apply molarity to it, because this is aqueous after all, so we can use molarity anytime. How many milliliters of 0.45 molar sodium hydroxide are required to neutralize so much of HCl? All right, everybody. Remember, what's always the first step? Is to get anything you can in the moles. Well, for sodium hydroxide, all I'm given is the molarity. I cannot get that into moles because that is moles over liters. But you see that combination again for hydrochloric acid, the volume and molarity. So that's always a 1-2 combo, everybody. So anytime you see molarity and volume, multiply the two together and you're going to get moles. Don't forget that, okay? So you're going to hear me say that again. Don't forget that. This is so repetitive. And you can totally feel confident in doing this because it's the same tools over and over again. So 0.250 liters of the hydrochloric acid times 0.89 moles of hydrochloric acid over 1 liter of hydrochloric acid. Okay, that's moles of A. And now from moles of A on to moles of B. And that is a 1-to-1 ratio from the balanced chemical equation, everybody. So times 1 mole of sodium hydroxide divided by 1 mole of the hydrochloric acid. And that gets us oh, you know what? We've got to do one more step, right? We still have to use the molarity there. All right, so my apologies. So Okay, moles of sodium hydroxide goes downstairs, liters goes upstairs, and that's going to be 0.45 and 1 on top. So when all is said and done, we get 0.494 liters of sodium hydroxide required. And the question's asking for milliliters, and so that's going to be 494 milliliters of sodium hydroxide required, everybody. All right, so this is a nice cumulative problem because it really utilizes the concept of molarity as a conversion factor, not once, but twice, everybody. All right then. So again, this is stoichiometry and neutralization reactions. The next specific application of stoichiometry pertains also to acid-base chemistry. And this is what we call the concept of standardization. Standardization is basically determining the concentration of an unknown. And to do this, we use the process known as titration. Okay, so titration is a general term where a solution of known concentration is used to determine the concentration of an unknown solution. In other words, we're going to standardize the unknown. We're going to find out its exact concentration. There are many different types of titration. A very common and specific type is also acid-base titration. In acid-base titration, a basic or acidic solution of known concentration is used to determine the concentration of an acidic or basic solution. All right. The analyte is what we're trying to find. This is the unknown. And the titrant is what we're going to be using to standardize the unknown. So this is the known concentration. So this is the solution of known concentration. All right. Let's get into the experimental setup. A typical titration has the following. Okay, a barrette is basically a very precise piece of glassware used to deliver small aliquots of liquid. And barrettes are usually pretty precise, up to 0.01 milliliters. Okay. In the barrette, typically goes the titrant, everybody. All right then. Inside the flask then goes two things. It goes the analyte and also what we call an indicator. And what an indicator's job is the following. It's going to provide a visual sign of when the titration is complete. Now we're going to talk about titrations, more complicated ones down the line, but for now, okay, an indicator's job again is to tell us when the titration is complete. And remember, this is acid-base neutralization after all, so this is going to tell us when the neutralization has occurred. So complete neutralization has occurred. Okay, and the visual sign is the indicator is going to change color. All right then, and again, you're going to do this so much in general chemistry lab, I promise you. It's one of the most traditional types of experiments we teach undergraduates. All right then, let's go ahead and jump into a typical acid-base standardization problem. And we got to get familiar with the terminology. 32.10 milliliters of 0.67 molar HCl was required to reach the equivalence point with 25 milliliters of magnesium hydroxide. Determine the concentration of the analyte. All right, first let's get some terminology out of the way. The equivalence point, everybody, is the point in the titration where complete neutralization has occurred. Okay, so the point in the titration where complete neutralization has occurred. So this is very important that you pay attention to these key words, because that tells you pretty much how much has reacted, everybody, when the reaction has complete. All right then. So, step one. Now, you always hear me, that you always want to get the moles as step one. And that's usually true, but what's even more important before that is that we have a balanced chemical equation, right? And so anytime you're doing a stoichiometry problem, make sure you know the balanced chemical equation or get it. Okay, so let's go ahead. So this is HCl, aqueous, plus MgOH2, aqueous. And that's going to go ahead and form H2O liquid and MgCl2 aqueous. Okay, we got to go ahead and balance it. So this is going to be 2 hydrochloric acids and 2 waters, everybody. Okay, why is that important? Because you just know that we're going to be using a multimole ratio from the balanced chemical equation. So it's imperative that you know the coefficients correctly. All right, now step 2. Get anything you can in the moles. So get all amounts possible into moles. All right, so we have the volume of magnesium hydroxide, and we can't do anything with that yet, right? So the only thing here is hydrochloric acid, and you see that we're given both the volume and molarity. So don't forget, right? You see that combination again, volume times molarity is going to get you moles, everybody. So let's go ahead and do this. So 0.3210 liters times 0.67 moles of HCl over 1 liter. Okay, and that gets us the moles of A. Okay, so once we get in moles of A, let's go ahead and get to moles of B. So it is a 2-to-1 ratio. So 1 magnesium hydroxide on top divided by 2 moles of hydrochloric acid on the bottom. And that's going to give us 0.011 moles of MgOH2. Okay, now the question is asking for the concentration of the analyte, the concentration of magnesium hydroxide basically. The only other value in the problem we haven't used it is the 25 milliliters. Remember that we want concentration, which is molarity. Molarity is moles over liters. We know the liters. It's given to us in the original problem as 25 milliliters. So that's going to be 0.02500 liters. And the moles of magnesium hydroxide we just solved for. And so when all is said and done, we're going to get an answer of 0.43 molar MgOH2. All right, so this is how you determine the concentration of unknown. This is how we standardize it using the concentration of a known substance. Okay, let me go ahead and summarize today's lecture then. The first take-home message is that when trying to define the concentration of a solution, the most common unit used is molarity. And again, molarity is moles of solute over liter of solution. Molarity can be used as a conversion factor in dimensional analysis problems, including dilution problems, double replacement precipitation reactions, acid-base neutralization, and acid-base standardization via titration. And finally, let's go over the basic steps and formats for doing general stoichiometry problems. So step 1, everybody, is to make sure you come up with the balanced chemical equation, if not provided for you already. So balanced chemical equation. Okay, step 2. Step 2 is to get all amounts you can in the moles. So get all amounts possible into moles. And remember, there are some common patterns that we have seen already, okay? So usually we can go from grams to moles, and that's going to be via molar mass. But another thing we've seen is using molarity, and that was volume times molarity is going to get you moles. All right, so again, that's using molarity, everybody, as a conversion factor. The first one here, we use molar mass as a conversion factor. All right then, and so that's going to get us into moles of A, everybody. And then, once you're in moles of A, you can go on to moles of B. And from moles of B, you can go on then to solve the problem. Sometimes the question asks for grams of B. Sometimes the question asks for volume of B. And again, if we're going to do grams of B, once again, that's going to be molar mass as a conversion factor. But if we're going to go to volume of B, we're going to be using simply molarity, again, as a conversion factor, everybody. Okay, so I hope that's a nice little summary of how to tackle general stoichiometry problems. Let's now work on some more sample problems. Okay, sample problem number 1. How many milliliters of 0.45 molar sodium hydroxide are required to neutralize 250 milliliters of 0.89 molar sulfuric acid? All right, so step 1, we don't have any balanced chemical equations, so let's go ahead and come up with it on our own. So sulfuric acid reacting with sodium hydroxide, that's going to go ahead and give us water and our salt, Na2SO4 aqueous. And let's go ahead and balance it. So we're going to be needing 2 of these, and of course 2 of those, everybody. All right, so step 1 is done. Step 2 is to get any quantities you can in the moles. Get in the moles. And remember, what are the possible combinations? Well, usually we go from grams to moles via molar mass, but you don't see any grams in this problem, do you? So the other alternative is to do volume times molarity, getting you in the moles. And here we have the volume and molarity for sulfuric acid. So that's going to be 0.250 liters times 0.89 moles of sulfuric acid over 1 liter. Okay, that gets us in the moles of A. And now we want to go to moles of B. So the moles to mole ratio is 1 sulfuric acid to 2 sodium hydroxide, so times 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. And finally, the question's asking for volume, right? We want to get now into milliliters. So to do that, we use molarity. Okay, so times 1 liter over 0.45 moles. That's going to give us a answer of 0.99 liters of the sodium hydroxide, which is going to be 990 milliliters required for neutralization to occur of the specified amount of sulfuric acid. All right then, so that's sample problem number 1. Let's now move on to sample problem number 2. How many grams? Okay, so right away I see grams, and so that's mass, and so I know for sure that I'm going to be using probably molar mass as a conversion factor. So mass via molar mass as conversion factor. All right, so how many grams of barium sulfate can form when so much sodium sulfate reacts with so much barium nitrate? All right, let's go ahead, everybody, and we see that we have both amounts of 2 reactants. So you know that this is a limiting reactant problem, right? So let's go ahead and go through it. So we're going to be using the smaller quantity method. Okay, so step 1, get the balanced chemical equation if it hasn't been provided to you already. So here we have to come up with it. So balanced chemical equation. Okay, so it's going to be sodium sulfate aqueous reacting with barium nitrate aqueous. And that's going to go on and form barium sulfate solid and sodium nitrate aqueous. All right, let's go ahead and balance this guy. So I'm going to be needing 2 of those, everybody, for our balanced chemical equation. All right, step 1 is complete. Step 2, everybody, yeah, you guys know the drill. Step 2 is to get all quantities you can into moles. So get into moles. And look here, for both of the reactants, for sodium sulfate, we have both the volume and the molarity. And for barium nitrate, we have the volume and the molarity. So volume times molarity gets us in the moles, everybody. Okay, so we're going to do this for each reactant, and we're going to see which one gives us the smaller theoretical yield for the product. All right, so let's work with sodium sulfate first. So 0.250 liters times 0.32 moles of sodium sulfate over 1 liter. Okay, that gets us in the moles of A. Now we go on to moles of B. So the mole to mole ratio between sodium sulfate and barium sulfate is 1 to 1. So 1 mole of barium sulfate over 1 mole of sodium sulfate. And that's going to give us 0.080 moles of barium sulfate. All right, so we're going to continue on with the smaller amount method for solving the limiting reactant problem, and we're going to repeat the process for the other reactant amount. 0.125 liters times 0.87 moles of barium nitrate divided by 1 liter. Okay, the mole to mole ratio between barium nitrate and barium sulfate is also 1 to 1. So that's 1 mole barium sulfate over 1 mole of barium nitrate. And that's going to give us 0.11 moles of barium sulfate. So using our smaller amount method, the theoretical yield is going to be 0.080 moles of product, and that's going to be 18.7 grams of barium sulfate formed, which means sodium sulfate is limiting. All right. Okay then, so again, this is a limiting reactant problem using molarity as a conversion factor. I hope you leave today's lesson feeling pretty confident and comfortable doing a stoichiometry problem. It seems like a lot of calculations, but if you follow the basic steps, you'll get it every time. Remember, step 1 is a balanced chemical equation, if not given to you already. And step 2 is going to be basically getting all the quantities you can in the moles. If you need to go from grams to moles, it's always molar mass. And if you need to go from volume to moles, it's always going to be molarity, everybody, for these 2 lectures. All right. Thank you, everybody, for using educator.com again, and I'll see you again next time.